We present QuCOOP, a framework for solving composite and binary parametrized optimization problems on adiabatic quantum computers. We are motivated by the fact that modern experimental adiabatic quantum computers, AQC devices for short, such as D-Wave only support quadratic unconstrained binary optimization problems, which severely limits their applicability. QuCOOP relieves this limitation and allows us to solve binary parametrized, possibly non-quadratic optimization problems using AQC. QuCOOP is versatile and can be applied to several computer vision problems such as shape matching and point set registration without correspondences. Many computer vision problems require complex objective functions to obtain accurate solutions. In rigid point set registration, given a reference and a template set of points, the goal is to determine the best rotation R and the best permutation P that jointly transform the template set and find correspondences with the reference set. This can be achieved by minimizing a squared objective involving R and P. In shape matching and quadratic assignment problems, the goal is to find the best permutation P that assigns the vertices of one shape to another such that the total cost or distance between corresponding vertices is minimized. This also can be achieved by minimizing a squared objective involving P. Unfortunately, these problems are NP-hard and challenging for classical optimization methods. Consider again the objective functions. We see they are quadratic, and, hence convex in their variables. However, these variables lie in complex non-convex sets. We observe that if we could parameterize the variables with binary variables, then we could turn the problem into optimizing a possibly non-quadratic composite function over binary variables. As AQC devices excel in binary optimization, QuCOOP enables the optimization of the resulting functions on AQC devices. AQC devices cannot directly solve our composite objective f of g of x, unless f is quadratic in G, x is binary, and G is linear in x. If G fails to be linear in x, QuCOOP iteratively linearizes it around the current parameter's guess, and solves a sequel of quadratic unconstrained binary optimization problems on the AQC device. QuCOOP is a three-step algorithm. First, the linearization of G is obtained by approximating it to the first order using Taylor expansion. Second, QuCOOP plugs this linear term into the original objective f, which results in a QUBO problem. To ensure that the linearized parameterization stays feasible, the user should design a problem-specific penalty function, quadratic in the linearization, that he adds to the QUBO objective. Lastly, QuCOOP samples the solution of the resulting QUBO on an adiabatic quantum computer. It can be shown, eventually with a recalibration of the solution, that the objective's values generated by QuCOOP are non-increasing. That is, QuCOOP effectively minimizes the original objective. To come back to the shape matching problem, in order to use QuCOOP for our objective, we need to find a binary parameterization for permutation matrices. We show that any permutation matrix P can be written as the product of n times n-1 over two binary parameterized transpositions in a fixed order. To get an intuition of it, we look at this example of permuting four elements. First, we should draw one out of three transpositions to fix the first element if it is misplaced. Then, we draw one out of two transpositions to fix the second element if it is misplaced. And finally, we should draw one out of one transposition to fix the last element if it is misplaced. Similarly, for the point set registration problem, we need to binary parameterize the rotation matrices. Rotation matrices can already be parameterized by non-redundant real parameters by leveraging the relation between the orthogonal Lie group and its algebra. Ultimately, we only need to binarize our rotation parameters. We achieve this by discretizing a search interval that we tighten in each iteration to refine the results. We next take a look at QuCOOP performance on different problems. We first implement QuCOOP using simulated instead of quantum annealing to evaluate its performance on large problems. We start with the quadratic assignment problem on the Kaplan dataset. We benchmark QuCOOP against dedicated classical solvers, namely FAQ and 2OPT, and also against the quantum-compatible competitor QMatch. Clearly, our QuCOOP is overall the best and outperforms its competitors by up to 5% lower energy error. Though its runtime is longer due to using simulated annealing, QuCOOP converges in around 5 iterations, whereas QMatch requires over 100 times more. On the D-Wave quantum annealer, QuCOOP is much faster than QMatch. On shape matching problems, QuCOOP showed a marginally better performance than QMatch, surpassing it by more than 0.01 lower geodesic errors. This is because QuCOOP optimally select and apply disjoint cycles, while in QMatch, this selection of disjoint cycles is done by hand and may be non-optimal. Note the monotone decrease of the objective function values of QuCOOP. We next present QuCOOP results on 2D and 3D rigid point set registration with correspondences not known in advance. We benchmark against the classical CPD algorithm. We see that QuCOOP can find reasonable correspondences, such that the rotation for aligning the point sets can still be found. CPD performs remarkably well on isometric sets, but, in contrary to our QuCOOP, shows difficulties when the sets have different number of points or describe different shapes. Lastly, we present numerical results of QuCOOP when it is implemented on D-Wave, a true quantum annealer. In line with the results of simulated annealing, QuCOOP successfully solves point set registration and QAP problems, finding valid permutation matrices with size up to n equals 12 the quantum annealer. The qubit connectivity on D-Wave limits us to small problems, as complex embeddings increase chain break probability and degrade solution quality. Thank you for listening.